In the previous video, we solved this particular question using a method I said was not the right method for it. It's kind of a brute force method of algebraically manipulating the expression as if it were real. But the complex exponents kind of behave differently from real exponents. So we are going to tackle it the right way today using the right method. So let's dive into that. But before that, the answer for the last question, the last solution yielded an answer, and that answer was actually right. This is the answer. Yes, this answer is right, and it's the principal solution to the question. There are other solutions to this. Just take this as, let's say, xy pair and xy pair. So let's say x plus yi or a plus bi. There are xy pairs, many xy pairs on this particular circle. A circle with radius 3.1018, and it has these xy pairs all around it, which are also solutions to the given expression here. So that said, we are done. We know that there are so many solutions for it, lying on one circle with a radius of 3.1018 units. So let's go ahead and do the needful. We will solve it using the correct approach. The right approach involves changing the base to an equivalent form in polar form. So this is the base, and this is the power. Now, to change the base to the equivalent form, we'll have to know that in polar form, there is an r and there is a theta. These are the information, this is the information we'll obtain from here. How do we obtain the r? The r simply defines the magnitude of the complex number. So r is equal to the magnitude of the complex number. So how do we find the magnitude? We just take the coefficients of the imaginary units and the real part, and we square them and add them and take the square root of them. So r should be equal to the square root of 1 squared plus 1 squared, which is root 2. We are done with r. Now, what would theta be? Theta, well, in this case, any complex number can be written as a plus bi, or you can say x plus yi. So it is equal to the inverse tangent of the imaginary part over the real part. Or you can use the other variables as well if you want. So this is what theta is supposed to be. So in this case, the a and b are 1 and 1. So 1 over 1 is 1. Inverse tangents of 1 is 45 degrees. And 45 degrees in radians is I over 4 radians. So we have gotten what we want. This and this. Now we can change it to the polar form easily. Let me write that. In the polar form, the base is now square root of 2 e raised to the 4 I over 4. But you see, the whole thing rotates around a circle. This thing rotates around a circle of radius root 2 units. So to cater for the rotation, whenever it reaches back to its original position, it cannot resets. And so if it covers an angle of 2 phi, it gets back to reset me, and then it kind of begins it all over again. So after it covers 2i radians around the circle, it will go back to its original position as if it hadn't moved yet. So the only way we can count them is to count how many 2 pi radians it has covered. So let's just put k to track the number of rotations or the number of cycles it has covered. So the 0th cycle, the first one, the second one, and so on. So this is the full form of the base. And let me just write the exponents. Now there's the exponent. From here, we'll just distribute the exponents to them. Root 2 raised to the power 1 is just still the same thing. And then e raised to the power whatever is on top here will be the same thing as well. Pi over 4 to pi k. But on this side, root 2 raised to the power negative I, we'll come back to it later. And e raised to the power this, we know that negative I times I is positive 1. So if it kind of multiplies the negative 1, then it all turns into 1, leaving us with just a real number. Pi over 4 plus 2i k. So notice that this is a real number and this is a real number. So we can group them together and group the complex numbers together too. So the 2 e to the power pi over 4 plus 2i k. And then we write the complex pi, which will be root 2 raised to the power negative 5 times e raised to the power I pi over 4 plus 2 pi k. Okay, so take a look at this variable. I'm going to rewrite it on the next page, but with this change in another part, into another part. So let's try and change this first. Let's do the change. Root 2 raised to the power negative I. To change this, you will first take the log of this, and then you take the antilog of it. I haven't taken the antilog of it. I'm kind of manipulating it, but it's in a different form. And then finally, take the antilog of it back. So you've come back to the same expression by taking the antilog, taking the log and taking the antilog of this. So this is it. Let me rewrite it here. Negative I natural log of root 2. So this is the value of that. Now let me write the full expression from here. This full expression. Root 2 e to the power I over 4 plus 2i k times, instead of root 2 raised to the power negative I, I'll write e raised to the power negative I natural log of root 2 and times e raised to the power I over 4 plus 2 k. And now that we have it this way, we can combine these two because the bases are the same. So we have root 2 e to the power I over 4 plus 2i 3 e to the power negative I over 4 plus 2 by k minus root natural over roots 2 closer by it. So this should be our final general solution to the problem. It's the most general form you can have for any k from 0, 1, 2 to infinity. So this captures all that there is about the expression. But the weakness of the other method is that it didn't have this term here. And that meant that it would have been wrong on a second attempt to find a second solution for it. So if I had decided to find for k equal to 1, either than the k equal to 0 and k equal to 2 or any other k, it would have been wrong because it didn't have this term. It only had this one. So this is the most general and comprehensive solution to it. Let me find for k equal to 0. So for k equal to 0, we would have square root of 2 and would have e raised to the power. And the 2 pi k will just go because k is 0 and we have 5 over 4. And we have e raised to the power I open bracket I over 4. The 2 pi k will just go because k is 0 and then you have just a minus a natural log of square root of 2. Good. So this particular thing over here matches exactly with what we had the last time with the other method. Just that the other method was just a clever trick that seemed to work for us, but not a good solution to the problem. Now, the numerical value of this will be the same as this. So, computing the results for this, we would have The same thing as we had the last time, 2.8079 plus 1.3. Okay, so this is the principal solution. Principal solution. Okay, but there are other solutions, as I already explained in the previous video, that there are other solutions which are on a circle with radius 3.1018 units. So yes, this is the end of the solution to the problem my friend sent to me. Thank you for watching.